Now we have understood the short term effects. Now let us look at what are the long term effect on the overall axial load deformation behavior. So what are the meaning of long term effects? Already we have discussed during the losses chapter. We are going to have concrete effects from shrinkage, creep and thermal expansion. So all three of them will induce some additional strains to concrete that we need to account in our calculations. And steel again will undergo relaxation. We have studied what is relaxation, and again steel also will undergo some thermal effect, that is also explained in clause 6.26 of IS 1343. So we need to say that we are assuming that the shrinkage and thermal strains has already occurred, followed by creep and relaxation. Of course, the one will affect on the other, but we are doing that in a cumulative effect. Okay. So we are saying that they are independently occurring, and then we can add those strains. Okay. Just to illustrate what are the effect of this long term effects I am saying. So let us see how do we account them in our actual calculations. Okay. So this is what we are saying, the total strain in the concrete considering the long term effect, which is basically equal to epsilon c, which is the net effect, total strain. In the total strain, this epsilon ct is nothing but the load induced, right, which is induced only from the load. Then you have shrinkage strains and thermal strains, right. Similarly, the total strain in the steel, if you have to include all the long term effect, I mean you have relaxation also. So here we are saying only the thermal strain. Okay. And epsilon st is the strain caused by the stress at the steel, and the total strain is basically epsilon. Similarly for pre-stressing steel. Okay. Pre-stressing steel is this. Okay. And epsilon Pd is the strain caused by the stress at the pre-stressing steel. Okay. Now, why is that we need to consider this long term effect? Okay. We have seen when we discuss the effect of creep, creep is going to produce additional strains in concrete the moment you have additional strain at a constant stress. So, effectively it is actually reducing the elastic modulus of the concrete. So, somehow I have to account for this effective elastic modulus, right. So, which is nothing but EC divided by 1 plus phi, which is phi is nothing but your creep factor that we have discussed, right. Now, strain corresponding to peak stress epsilon prime Cc, in this case if you see here, we instead of epsilon prime C we have to use epsilon prime Cc, which is nothing but your f prime C by Ec, and we have to use basically the stress there is no change, but the strain is increasing. That means your peak stress is actually happening at a much larger strain, right. So, that is what we are seeing. So, the moment you get your EC, that is ECE here it should be, right, EC, the effective modulus, right. Similarly, the same effect for pre-stressing steel also. Pre-stressing steel in relaxation, what is that? At constant strain, to keep the pre-stressing steel at a constant strain, now I do not need to apply the same level of stress. The stress that is required to keep it at constant strain is going to keep coming down, right. So, again what is the effect of that? It is in effect it is actually softening the steel, or the elastic modulus of steel is getting reduced. So, that is what we say, the effective elastic modulus is nothing but 1 minus relaxation effect into the actual elastic modulus of the pre-stressing steel. So, if you assume 200 initially, because of the relaxation it will reduce to maybe 0.9 or 0.95 times your EP, which is your original elastic modulus of the steel. Now, let us look at how these effects are considered. So, again I am taking this partially pre-stressed section that we have discussed previously. Now, we are going to derive the load deformation response for a partially pre-stressed section, and with the steel of 1350 and 395 mm square and concrete grade of 30 megapascal and yield strength of non-pre-stressed steel with 500 megapascal, and initial stretching stress we have already said 1240, and creep coefficient is 2.2. This is what will help me to establish this ECE, right, which is EC divided by 1 plus V, and shrinkage strain is 0.0002 strain, and sign convention is taken as tension is positive and compression is negative. Now, let us do the same calculation for a strain of 0.001 in compression. What is the total strain? The total strain is epsilon C in compression minus, because the actual strain will be epsilon Ct plus epsilon Sh. Now here I want to calculate what is the total strain causing the stress, which is your epsilon Ct. That means it should be epsilon C minus epsilon Sh. So epsilon C is minus 0.001 minus of your compressive strain. Shrinkage strains are negative 0.0004. If you take it, the net strain becomes 0.0006 in compression, right. Now, what are the reduced effective modulus for the steel due to creep, which is EC by 1 plus phi, again 5000 square root of FCK by 1 plus phi. Now, how do I get your FCK? 1.25 times, because you are given only the cylinder strength. Cylinder strength has to be converted to cube strength minus the standard deviation that we assume will give me the actual characteristic strength. So, if you plug in that value, you get for a phi of 2.2 only the modulus of 9310 megapascal. That means due to creep, the concrete has softened quite a bit, right. So, EC originally is 5000, that has reduced significantly, right. So, then the strain corresponding to peak stress is going to be F prime C by ECE, that is going to give me a value of 0.004, and though the stress is this, the strain corresponding to peak stress is now, originally typically it is 0.002. Now, because the creep effect, because the material has softened, now the peak stress is happening at strain of 0.004 instead of 0.002. Now, reduce effective modulus for relaxation, that you know I am assuming 5% relaxation. So, elastic modulus of the pre-stressing steel reduces from 200 gigapascal to 190 gigapascal. Okay, now we are doing the calculation. So, strain in the non-pre-stress steel as per the compatibility condition is going to be again same, epsilon S is equal to epsilon C. We have taken epsilon C to be 0.001. So, epsilon S also will be same. Delta epsilon P is 0.0062, which we have already calculated that in the previous example, and the total strain is going to be epsilon C plus this. So, it is going to be 0.0052. Now, you see what is the stress in the pre-stressing steel, and I need to use the reduced elastic modulus. So, you see I get a stress of 988 megapascal in tension, and stress in the non-pre-stress steel is going to be 200 megapascal, same as that of what we have calculated, because it is not going to have any effect on relaxation, is not going to have any effect on your non-pre-stress steel, but it will have effect only on the pre-stressing steel, right. Now, what is the stress in the concrete? Now, I have to use epsilon prime C of 0.004 and actual strain in concrete of 0.0006, you get stress of only 8.32 megapascal. So, you substitute in your axial load, you get a value of 1363 kilonewton. So, this is the total compression load corresponding to a strain of 0.0006 only induced by stress, right. So, like that if we do the calculation, so this is what we did, and for a net strain of 0.001, the load induced stress is 0.0006, because I am also adding the shrinkage strain, which is again 0.0004, so it adds up to 0.001, and epsilon P becomes 0.0052, and strain in the steel still remains 0.001, and the stress in the concrete is very low value. Stress in the steel is 988, stress in the steel is 200 in compression. Now, you see here the deformation is going to be epsilon Ct multiplied by, this is basically epsilon Ct multiplied by L, okay, that is your delta L, right. So, you get 0.6 millimeter, and the load resistance is 1362.8 kilonewton, right. So, you can repeat the same process for different values of epsilon C, and you get your net epsilon Ct and plug it in your calculations, constant equations. Only thing is two things, because of long term effects, elastic modulus of pre-stressing steel reduces, elastic modulus of concrete reduces, and the strain at which it is going to reach the peak stress is also going to increase. So, all these effects you consider, and you can generate your entire load deformation behavior again, right. So, if you plot this, the red color is a short term effect that we have previously considered. With considering the long term effect, if you look at it, you see here the stiffness, basically the slope is nothing but your stiffness. So, you can see here in both tension and compression, because the elastic modulus of concrete has reduced, the material has actually softened. Because of that, the stiffness of the member has come down, right. So, it is less stiffer. If you consider the long term effects, the member response becomes less stiffer. But one benefit that you can see from considering the long term effect, what is that? Your compression load actually goes up. So, in a way, it is offsetting the detrimental effect of pre-stressing on the compression side, right. So, this is one of the I should say beneficial effects of considering long term effect in this example that what we have considered. But there is a marginal reduction increase in your cracking load if you plug in all your values and use the same formulation for calculating the entire load deformation. And this stiffness also there is a reduction, okay. Again this is the slope, okay. And you see here, or I should say this is only the steel stiffness, so small reduction is there, and there is no change in your ultimate strength, because both the blue curve and red color is having almost reaching the same capacity in tension. So, you can conclude in compression the stiffness is lesser when the long term losses are considered. In compression again the peak load is slightly higher when the long term losses are considered. The tensile strength does not really change, even the cracking strength does not really change appreciably, right. So, now this is the summary. Now, we can also for quick calculations, if you are in the elastic regime, that means before cracking, in compression let us say that your stress values are less than 40% of your compressive strength, then you can assume the entire load deformation behavior to be linear, right, because in compression the material has not become non-linear yet. In tension it is not cracked, so you can assume it to be linear. So, this is a linear regime. So, from here to here we can consider this as a linear elastic region that you have considered. So, if you want to do the calculations in this region quickly, we can form a very simplified expression for calculating the stresses or calculating the load versus deformation response, right. So, you see here this is the basic equation from equilibrium: stress in the concrete multiplied by area of concrete, which is Pc again, stress in the steel multiplied by area of steel, which is Ps, stress in the pre-stressing steel multiplied by area of pre-stressing steel, which is nothing but your Pp, right. Now, this is the problem is the stresses we do not know how to calculate. If I assume that this material response is to be elastic, then I can always write stress as elastic modulus multiplied by strain. So, that is what we are going to do, and we know the compatibility condition. So, that is what people did. So, we have taken this equilibrium equation and we are assuming that we are in the linear elastic regime. So, for short term losses, there is no so you can replace the FCS EC into epsilon C, you can replace FS as ES into epsilon S, you can replace FP as EP into epsilon P. Now, we know the compatible conditions: epsilon C is equal to epsilon S, epsilon P is equal to epsilon C plus delta epsilon P, where delta epsilon P is nothing but your initial strain. Then you can form an expression between axial load and the strain directly, right. So, you can plug in all your compatibility equations, then finally you can everything can be expressed, load can be expressed in terms of the assumed strain value like this epsilon C. Okay, this is a closed form equation to find strain. So, if you give me load, I can find out what is the strain that is causing that particular load, right. So, this is one closed form equation. Now, for long term losses, again in this equation we know that epsilon C comprises of load, this is load effect, and this is shrinkage, and this is thermal. Similarly, for steel, you will normal non-prestressed steel, we consider only the thermal effects. For prestressing steel, we consider the again thermal effects. So, if you substitute that all of them epsilon C, you again from this relationship you can find this very simple expression for calculating the for a particular load what is the strain, or in other words for particular strain what is the load it is resisting. So, in this way, for linear elastic regime, a simplified expression also can be developed. Okay, let us again quickly go through one example, again same problem, and I am taking 1350 megapascal millimeter square of non-prestressed steel and prestressing steel AP of 395. So, this is AS. Okay. Now, let us see how to use this equation to quickly do some calculations. What are the things that we are going to do? We want to calculate at the the stresses in all the material, stresses in the concrete, stresses in the steel, stresses in the prestressing steel at different strain condition. That means a decompression point means when the axial load is 0, that is a decompression condition, and when the axial load is 2500 kilonewton, and a grade of concrete is 30 megapascal, right, and yield strength is 500 megapascal, all this thing that we have already given. So, let us see now how to use this formula, right. We have already developed this expression, right. So, initial stretching is 1240 multiplied by 395 gives me what is the force that we have applied, and elastic modulus of concrete I can calculate using 5000 square root of FCK, right. So, you get this value at axial load n equal to 0, then you get your n is equal to 0 means this is the equilibrium condition. So, it is a linear relationship. So, what we can do is we can calculate what is the strain at which the n is equal to 0. So, it is a very small strain of 0.000095, actually there is no axial load in the cross section, right. So, then again for a load of 2500 kilonewton, now n is given, now again we are calculating what is the strain will be realized in the concrete when the load applied is 2500 kilonewton. So, if you substitute that, you will find that you get a strain of 0.00039. Okay, this is an axial load that is corresponding to that, right. So, in this way, using simplified expressions, I can calculate, assuming that the system is inelastic, I can quickly for a particular load what is the strain, or for a particular strain what is the load that is being resisted, right. So, these are the things that are related to the axial load behavior. So, we can summarize the discussions that what we have had. So, we have seen that the pre-stressing is going to increase the cracking load significantly, and you see that pure pre-stress section had highest cracking load, followed by partially pre-stress section, followed by the RC. So, if you want high cracking load, you need to apply pre-stressing, and pre-stressing curve shifts from the origin. Okay, that means even when there is no externally applied load, there are some strains in the pre-stressed section. So, that is why when n is equal to 0, you will find that there will be some deformation. So, that means when I do the because of pre-stressing, the member will always have some strains and deformations, right. So, there is a for a pre-stressed member, there is a compressive deformation in the absence of any external axial force. For a given tension load, the deformation of the pre-stressed member is smaller. That means, we have seen that pre-stressing helps me to reduce the deformation in a member. Okay. So, if your service load levels are fixed, then going for pre-stressing will help you to reduce the amount of deformation that you will have in the tension loads. Typically, flexure will create tension. So, deflections are created by flexure. In this case, this is also flexure is actually governed by tension behavior, right. So, pre-stressing, that is the reason we do pre-stressing for long span members. Again, for a given compressive load, the deformation of the pre-stressed member is larger. That means, pre-stressing is detrimental for response under compression. If your member is compression dominant behavior, in fact, pre-stressing should not be done, right. That is why in columns typically we do not do pre-stressing, right. We do pre-stressing only in horizontal members like beams, slabs and so on, right. For a partially pre-stressed section with the same ultimate strength, the axial load versus deformation curve will lie between the curves of pre-stressed and non-pre-stressed section that we have already explained in the load deformation behavior, right. So, with that we can summarize what we have discussed. In this lecture, we have explained the basic mechanism of pre-stressed concrete members under axial load, both tension and compression. We have developed the axial load deformation response for pre-stressed members with different reinforcement combinations. We have also explained what is the effect of time dependent losses in axial behavior. We also explained the load deformation response using simple linear elastic response in the uncracked regime of the pre-stress section, right. So, with that this module 3 will be done. Thank you for your patient listening. We will look at the flexural chapter in the next week. Thank you.